So let's go to for example, the PyTorch home page. Getting started, it has a lot of variants. For example, PyTorch is available in different variants. It is available for Linux, Mac, as well as Windows. You can install it through Conda, Pip, libtorch, or you can have source. It is available in Python as well as in C++ and Java. And if you have CUDA or GPU kind of support, you can select the variants for that. In my case, I am installing this only for a CPU variant, and I have these kind of the selections. You can change the selection, then you get different. And also, I'm going to install it through Conda. So first of all, before actually installing it through Conda, let me make an environment for it, a new environment. So let me make an environment, for example, Conda, create, name, let's say the environment name, let's say PyTorch 2. I'm writing PyTorch 2 because I already have an environment PyTorch with PT. So let me make another environment just to go through the whole process. Making different environments for different kind of tasks is always good in Python. So I will recommend to make this practice, so making environments for different environments to stay away from the clashes and kind of the incompatibilities of different packages in Python. So let's make this environment. So yes. Okay. Now let's activate this environment. Conda activate PT PyTorch 2. Let's say that's activated. Now we have to actually install PyTorch here. So let's go and see if we want to install through Conda. If we want to install through pip, we have to install pip first in the new environment. So let's install it through Conda. And let's go there and we install it through Conda. One other thing that you might have drive on Windows, for example, you may have drive permissions, writing permissions. So it is okay to use local just to set the writing permissions on the directory. So then you press enter, and from the internet it will be actually fetching the required package, and it will be installing it for you. So let's go through the whole process and see how it goes. Yeah, so it's doing some required stuff for installation. So let's wait for it and see how it goes. It may take a couple of minutes to do that. So yeah. So what it basically does is it actually use some cached copy of that. So it actually does it very quickly. And the reason is I already have installed variant of PyTorch in another kind of environment. In your case, if you're going to install it for the very first time, it may take a couple of minutes to download the package and then install. So that should be perfectly okay. So let's test whether it has been installed or not. Let's test that on Jupyter Notebook, but in this new environment, you may not have Jupyter installed already, and maybe we want to install Jupyter through pip. So let's install pip first. Conda install pip. So it may take a couple of minutes to do that. So let's install that. Yeah. So already installed. So then let's install, for example, pip install Jupyter, just to, yeah, it may take a couple of minutes to do that. So yeah, so it's almost there. So let's wait for it. So it's about to end. It's installing Jupyter for us. Maybe if you're working in another coding environment, you may not need Jupyter, but um, for the beginners, I will recommend to stay on Jupyter and make other environments, different environments for different tasks. For example, if you want to work in TensorFlow, make a different environment for that. If you want to work in MaxNet, make a different environment. If you are going to work with PyTorch, make a different environment. That's recommendation, and things will become a lot easier. So everything is set. One other thing, you may want to access a lot of data sets in PyTorch, for example, image data sets. For that, we may need another helper package, Torch Vision. So let's install that as well. Pip install Torch Vision. So that's for vision data sets. Yeah. So everything's set. Let's now check our installation, Jupyter Notebook. Let's just open it up and do some of the very basic stuff. So let's have Python 3. And so one problem that is normally there on Windows, for example, this was there in when I installed MaxNet on my system. Maybe you get the same error as well. Is the pywin32 error. So that is there. Sometimes it is there. So that is just to correct the variant. This error may not be there if you're working in Linux or Mac. So let's go back and fix this error by installing a little older version of pywin32. So let's leave that. Let's end this and let's finish this by Control-C on Windows. And yeah, it's about to, it's shutting down the terminals. So yeah, so let's now install pip install pywin32. In my case, I have Python 3.8. Version 2 to 5 is working perfectly. So let's install that. It will uninstall the already installed 2 to 8 version and will then install 2 to 5, which actually pings this DLL. So now let's Jupyter Notebook. So now let's open up this, and I guess there will be no kernel error. Yeah, no error there. So let's name it as PyTorch hello world. So let's hide this. Let's see, import torch. If everything is working fine, that's the torch. And let's say we have tensor x torch dot zeros. Let's say 3 by 3, and you might have this tensor available. So which means all set. Torch is installed. Torch Vision should have also been installed, no problem. Here in for example, just to compare, in MaxNet we normally work in the package ND for arrays. Here we have to work in the package Torch, and it will generate the n-dimensional arrays are normally tensors. So we can work with tensors just like we are working with, for example, NumPy arrays. So for example, x is equal to torch dot rand, for example, random, let's say 4 by 3, let's say this. We can have, we can print this, we can have shapes for that, and we can convert this tensor to numpy to tensor, not a big deal. I mean, there are, for example, let's print this x dot size. Let's print that size. So for example, this function actually tells what's the size of this torch. So this is 4 by 3. You can save that. You can have, for example, multiple tensors. For example, y equals torch dot rand maybe 4 by 3. And then you can simply add the two tensor x plus y, and you can just print them out, the result, just like you're working with NumPy arrays. And you can go back and forth. For example, you can convert this to NumPy array, you can index, you can slice and do everything just like you're doing with NumPy. So for example, if you want to convert this x to NumPy, for example, z equals x dot NumPy. So now this z will no longer be a torch tensor, it will be a NumPy array. So, so that's a NumPy array, n-dimensional NumPy array. Okay, let's take a very simple example to understand the automatic differentiation, particularly in PyTorch. Let's say we have a loss function or some function, let's say f, some function of parameters, let's say a and b. And let's say this function is 2 times a square minus, let's say, 4 times b square. Let's say that's our function. You can think of this function as a loss function. This is some loss function where the parameters are a and b. And this loss function is basically 2a square minus 4b square. And in all the cases in neural networks and in machine learning, we need to optimize this loss. So what we really do is we take the loss function and we compute its derivative with respect to each parameter individually. So let's think about the loss, derivative of the loss with respect to a, and with respect to a, the loss become 4a. So that's the loss value, the gradient or the partial derivative of loss with respect to a. Similarly, the partial derivative with respect to b, a becomes minus 8b. So that's how the gradient is being, that's how the partial derivatives are computed. Gradient, on the other hand, is just the vector of partial derivatives. Now think that if we have the value of a, let's say the value of a is 2, and the value of b is, let's say, 6, then what is the gradient value? What is the value of the gradient? Of what is the value of the each partial derivative of the loss? Well, the partial derivative with respect to a becomes 4 times 2, and that becomes 8. And the partial derivative with respect to b, that becomes minus 8 times 6, and that becomes minus 48. Yeah. So that is what that is what the differentiation we did with formulae, or I mean with the mathematics behind. Let's see how can we solve this differentiation problem if you want to do this differentiation automatically using PyTorch. Obviously, for that you have to install PyTorch. Here is an example. So let's see. Import, for example, import torch. I'm assuming you have already installed Torch, so import Torch. We have to define the parameters as torch tensors or torch variables. Torch.tensor, and let's say the value here is 2. That's the value, the initial value of parameters. And what we have to set is this parameter required gradient true. So whenever we define a value or a variable or a tensor, we have to set required gradient true if that is the parameter with respect to which we want to compute the gradient of the loss function. So all the parameters of any neural network, all the parameters, when they are declared, this variable has to be set true if you want automatic differentiation of the loss function with respect to those. Now let's say b is torch.tensor, and the initial value, let's say 4, and again let's say requires gradient is set to be true. So all good. Here, don't worry about tensor. You can think think of tensors as just the NumPy arrays, multidimensional array. Technically, a tensor is an array having dimensions more than 2. That's a technical name of tensor. But don't worry, it's just a multidimensional array. Here, this array is just a single number. But that's the way you can define any tensor of any dimensions in Torch. And defining the tensors in NumPy has a different syntax. Okay, now let's define a loss function, our loss function. Let's say that is 2 static a square and minus, let's say, 4 times b square. Let's say that's our loss function. So now if we apply this value of a and b into the loss and we just call the method backward, this command l.backward, basically the function backward, will compute the gradient and save the gradient in the variables that requires gradient. So for example, what is the value of the gradient with respect to a, or basically the partial derivative with respect to a? So that is a dot grade dot data. And if you see in this case, the value is 8, which is what it should be. So print, for example, and b dot grade dot data. If you see the gradient value of a and b, so the gradient value of a is 8 and the gradient value of b is 32, because this b value is 4. In our example, we took the value 6. So it was, in the case of 6, it becomes 48. But anyways, now this is the loss function. And all the parameters that requires the gradient true, when you call l.backward, the gradient of the loss function, whatever that function on which the backward is called, the gradient with respect to each parameter is automatically computed and saved in the property a.grade and b.grade respectively. And I mean, no mathematics at all, no need to write any backpropagation, no need to write any gradient computations. Each and everything will be happened automatically. And this simple example actually it's a very simple example, but it extends to very, very complicated and powerful architecture and neural networks, that you just define the loss, you define your parameters, you define the loss function, and then you just define the forward pass. Once you have a forward pass, you have the loss computation, you're done with computing loss. Then you need not to go step by step backward to compute the derivatives of all the parameters at every layer. This L or the loss dot backward will do that stuff for you. And that's a lot of packages, they actually offer automatic differentiation, and Torch is one of those. How great. Yeah, so that was a simple example. Let's dive in and build a recurrent neural network using this automatic differentiation. Again, remember, we just have to define the forward pass, and we have to define the loss function, and we have to define the parameters for which we need gradients, and we also have to define the gradient descent step, but we need not to compute gradients at all on our own. This dot backward function will do it for ourselves. So let's write a fairly involved example just for our understanding, and build a recurrent neural network on our own using automatic differentiation. Hope to see you in the next video.